Okay guys, in this second video, let's talk about some of these definitions that we sort of implicitly started to use already. Roster notation, set builder notation, and descriptive notation or description notation. So first of all, roster notation. If you think about what a roster is, like the first time I heard the word roster was when I was on a soccer team and you have the roster, and the roster is the list of all the players, right? And that's all a roster is. It's just a list. So in the back of your mind, you can think roster notation means you're making a list. So this would be an example. That's a set 1, 2, and 3. The set of those three things. The elements are 1, 2, and 3. And we know it's a set because we use that fancy curly bracket to tell us, oh, I'm about to tell you what a set is and what belongs in it. That's the things that I write down with commas in between the elements. Now, sometimes I want to have an indication that I'm going to continue a pattern forever and have maybe like an infinite set. Infinite set just means that there are infinitely many things inside of it. And so we can do that with these little dots. We saw that when we were writing the natural numbers earlier, right? In fact, this set here is the natural numbers right here. This is another way of writing the natural numbers. So the dots indicate that you're going to keep going forever. Okay, so that's roster notation. Next is set builder notation. This is the one that trips people up a lot, but this is really actually not so bad once you get the hang of it. Let's look at this first example. So this says all x such that x is a natural number. That's how you read this. Okay, so let's unpack that. So again, the curly bracket tells me I'm about to tell what a set is, and then we know x is x. This line right here, the way we read that is such that. And what that, such that. And the purpose of that line is to tell us I'm about to give a condition for being in the set. So it's every x such that x is something. And what is the condition? In this case, it's x has to be a natural number. So x, remember this symbol we saw a little bit earlier? This guy right here means is inside, or is an element of, right? Or is in, or is in an element of. So every x that's an element of the natural numbers, that's what's going to go in this set. Here's another example. All x such that x is an even counting number. I'm just repeating what's written there. And what would that be? So if I was to change this now from set builder notation to roster notation, that would look something like this. Dots to indicate that it goes on forever. Actually, no, I'm sorry, I did that in the wrong order. Even counting numbers. Counting numbers are things like 1, 2, 3, 4, 5. But if it's even, that means only 2, 4, 6, 8, etc., right? And then the dots to indicate that I'm going to go on forever. So here, this first version, this would be set builder notation. And the second one is roster notation. Now, why the heck do we care about set builder notation? And the answer is because sometimes it's really hard to write something as a list, or in some cases it can even be impossible. And here's an example of something that's impossible: the rational numbers. Think about it. How would you write all fractions? Let's just try. Okay, let's try to write a list of it. Okay, I'm gonna write things like a half. Okay, for sure. Things like a third. Things like a fourth, and a fifth. Okay, there's a whole bunch of those guys. But that's not the whole list, right? There's also things like 2/3 and 2/4 and 2/5 and etc. And then what about 3? And this is going to be really hard to make a list. In fact, it's how am I going to account for every single possible fraction? There's no way to make a list of all those things, right? So what am I going to do? I'm going to make this list. Instead of writing it as a list, I can build the set using set builder notation. Here's how we do it. We're going to start the same way as always. Something such that something. But I'm going to use a little trick. Instead of x, I'm going to say a over b, because a over b is a fraction, right? So it's everything that's of this form, a over b, such that a and b are integers. They're integers. So a and b are integers. And also, we can't divide by 0, so we should specify b cannot be 0, because I don't want to have a b in the denominator, right? I don't want to have 0 in the denominator, because if you ever took algebra, you know when you divide by 0, the universe implodes upon itself. Okay, so this is saying everything of this form, a over b, where A and B are integers. That's how we describe or build the set of rational numbers. Okay, if that is confusing, again, just pause it until it makes sense to you. And I think the book probably has something to say about that as well. Or you can look up the rational numbers set builder notation on YouTube if you want more information. Okay, let's move on. Now, description or descriptive notation, that's really the easiest, I think, of the three. It's just you describe what belongs in the set. So here is another way of saying the natural numbers, or the integers rather. Just say what belongs in there. So yeah, it's pretty self-explanatory, right? You just write out the English for the set that you want. So I could say the rational numbers. That's another way of saying it. Or the set, I should say a set. The set of rational numbers. Assuming you already know what rational numbers are. So this is the same thing as that set right here, which is the same thing as that set right there. There's all three different notations of writing that same thing. Okay, so now we know the rules, right? We know these three different notations for writing sets. Let's try it out. And whenever we try out questions, try them out on your own before you continue to watch the video and see if you can figure it out without my help first. By the way, classwork is just that. All you're doing is just turning in the problems that we're doing here together. And so there's no question about getting it right or wrong because I'm giving you all the correct answers. It's just a matter of, are you tracking with the class? It's just our way of making sure that you're not falling behind, really. Okay, so classwork is just to turn in these questions that we're doing together here. Let's start with number one. Okay, so I'm assuming you tried it out. I'm just gonna blast through these things. Normally, if I'm teaching this class in person, then I would give some time to let you try it out first. But since you're watching this video after the fact, just pause, try it first. So this is all x such that x is a natural number and less than 5. So which numbers belong in that category? Well, first of all, it says to write it in roster notation. That means I'm going to start with a bracket to indicate I'm starting the list for the set. And then I'm going to write everything that's in there. Natural numbers less than 5. Natural numbers, remember, start with 1, right? So all natural numbers 4, 5. Oh, wait a minute. I did that first. 5 is not a natural number that's less than 5, right? 5 is not less than 5. So I went one too far. I should stop at 4. And that's my set right there. Let's alternate between red and blue here. So number 2, all x such that x is an integer this time. It's greater than or equal to -3 and less than or equal to +3. Okay, so that would be, again, bracket to indicate I'm starting. Integers include positive and negatives, but it can't be past -3. So -3, -2, -1, 0, 1, 2, and it can't be past +3 because it's less than or equal to 3. So that's that. Okay, number 3. Let's do that over here. What is it equal to? Okay, all x such that x is a whole number. Remember, whole numbers are counting numbers plus 0. And x is bigger than or equal to -3 and less than +3. So this part looks the same as the previous question. But because I'm only talking about whole numbers, I don't get any of the negatives. So it's going to start from 0 this time. 0, 1, 2, and 3, and that's it. Okay, next. All x such that x is a letter in the word math. Okay, so what are the letters in the word math? Again, start the set. And the letters are M, A, T, and H. That's the set. It's got 4 elements. The M, the A, the T, and the H. It's a 4-element set. And those letters are the elements. Okay, next. The set of all letters in the phrase by Felicia. That's equal to. Okay, so what are the letters in this set? Well, you've got a B, you've got a Y, you've got an E, you got an F. And then next you have another E, but I already have E. When we're talking about sets, either something is in the set or it's not. There's no point in putting it in the set twice. It's either there once or it's not in there. So I don't have to write E again. I only include it one time. So B, Y, E, F. Next is L, I, C. And then next will be another I. But again, I have I already. So there's no point in writing it again. And an A. So I asked myself now, how many elements are there in this set? And the answer is, let's count, there's 1, 2, 3, 4, 5, 6, 7, 8 things. Eight elements in that set. And those elements are those letters B, Y, E, F, L, I, C, and A. Okay, moving on to the next set of questions, 6, 7, 8. This time we are going from roster notation back to set builder notation. Erase all this stuff. So distract myself. Okay, so let's start with this first one, number 6. 1, 2, 3, 4, 5. How would you rate that set builder notation? We'll start with the usual. Start all x such that x is, looking at 1, 2, 3, 4, 5, it looks like those are natural numbers. And I want them to be less than or equal to 5. So I'm going to say less than or equal to 5. Now, some people ask me, is there another way to write that? And the answer is yes. Let's say, for instance, you want to have less than instead of less than or equal to. And you could do that. You could just change this to a 6 instead. Integers less than 6. Yeah, that works. Or natural numbers, I mean. Less than 6. Yeah, same thing. Personally, I like less than or equal to because that just kind of seems simpler to me. But you can take your pick which you prefer. I like this color blue. Okay, so number 7, -1, -2, -1, 0, 1, 2, and onwards forever after that. So this is kind of similar to something we saw earlier. This would be all x such that x. This time you want negatives, so I'm going to say integers. And I want my x to be bigger than or equal to -2. I don't want it to go below -2. And other than that, it can go on forever. So that's really the only bound I need. I just need it to be bigger than or equal to -2. Now, some people take issue with the way I wrote that just now. So there's actually multiple ways to write this. And here's another common alternative, which means the exact same thing, and both are acceptable answers. You can say all x such that x is an integer, but you can say x is bigger than or equal to -2, and it means the exact same thing. Okay. Now on to number 8. We're back at red. So the set of all integers except for 5. So this time we're starting from description notation, and we're writing it as a, set builder notation. Yeah, so x such that x is an integer, but it's not equal to 5, so it's not 5. Everything except for 5. Yeah, that's a nice clean way of writing that set without having to make a list. Okay. Let's see, should we cut this off? Yeah, let's cut this video off here. And then in the final video, we'll talk about subsets and we'll talk about cardinality and equal and equivalent. We'll just wrap up everything else up.